Have you ever stopped to think about that massive, invisible network that pretty much powers our entire world? It's this incredibly delicate dance of electricity, and it's all protected by a system that works so fast you never even know it's there. So today, we're going to pull back the curtain on these silent guardians of our electrical grid.
It's a really good question, isn't it? I mean, it all seems so fragile. A single storm, one stray tree branch, and you'd think millions of people would suddenly be plunged into darkness. But they're usually not. And that is not luck. It's because of an unbelievably fast, intelligent, and powerful defense system that's built right into the grid itself.
Okay, so let's dive into this by first understanding the problem that our grid is constantly, and I mean constantly facing. What exactly is happening in that split second when something goes horribly wrong?
Well, in the world of power engineering, they have a name for it, a fault. And it's basically the grid's version of a short circuit, but on a massive scale. It's an unplanned, often pretty violent, rerouting of electrical energy that the system was just never, ever designed to handle.
And when I say abnormal flow, the scale is just staggering. A fault current can be literally thousands of times greater than the normal current that's supposed to be there. So try to imagine a little garden hose suddenly trying to handle the full explosive force of a city fire hydrant. That's the kind of power we are talking about, and it is incredibly destructive.
So here's the kicker. If you let that fault run wild for even a fraction of a second, the consequences are, well, they're disastrous. That immense energy just melts equipment, it can start fires, and it can trigger a domino effect, what's called a cascading failure that takes down huge sections of the grid. This is exactly how you get from one fallen tree to an entire city-wide blackout.
So how on earth does the grid save itself from this constant threat? Well, it uses something you can think of as a high-speed nervous system, one that's capable of sensing danger and reacting way before the damage becomes catastrophic. Let's take a look at how it works.
At the very heart of this system is a device called a protective relay. Now, a relay doesn't stop a fault from happening in the first place. You can't stop lightning. But what it does do is limit the damage. Think of it as the brain, or maybe the nerve ending of the grid. It senses the danger and immediately takes action.
So how does it do it? Well, the relay's job can really be broken down into 3 simple steps. First, it's constantly measuring the pulse of the grid through its sensors. Second, it compares those live readings to what it knows is normal and safe. And third, if those numbers suddenly go haywire, it decides to act. And all of this entire process, happens in just a few thousandths of a second. It's just mind-bogglingly fast.
Okay, but wait a minute. The grid is enormous. It's huge. How does this system know exactly where the problem is so it can avoid shutting down way more than is absolutely necessary? Well, it does it by breaking the entire network down into these manageable little pieces.
The grid is divided up into what are called zones of protection. Every single critical piece of equipment, every generator, every transformer, every major power line has its own dedicated protection zone. And these zones, they overlap, making sure there are absolutely no blind spots. It's kind of like having specific nerves for each part of your body, so the system can isolate the source of the pain with just surgical precision.
And to make the whole thing incredibly reliable, there are layers. You've got your main protection, which is the instant, frontline response for a fault in its own zone. But what if it fails for some reason? That's where backup system comes in. It's kind of watching from a distance, and it's time delayed. It gives the main system a chance to do its job, but if it doesn't, the backup system jumps in to clear the fault, making sure nothing gets missed.
These incredible devices haven't always been the lightning-fast microcomputers they are today. Their evolution actually mirrors the story of modern technology itself almost perfectly.
Yeah, over the last century, we've basically seen 3 major generations. We started with these purely mechanical devices, gears and coils. Then we moved to early electronics for transistors. And finally, we've arrived in the digital age with these incredibly powerful microprocessors.
The earliest relays were just these amazing pieces of engineering. They literally used the magnetic force from the fault current itself to physically spin a disk or pull a lever that would trip a circuit. Super clever, super tough, but by today's standards, very, very slow and bulky. Now, you compare that to today's numerical relays, and it's a completely different world. These things are essentially specialized, hardened computers. They use complex software algorithms to analyze the grid, and they're not just faster and more accurate.
One single little box can perform dozens of different protection and monitoring functions that used to require a whole wall full of those old mechanical relays.
Okay, so we've looked at the problem, and we've looked at the technology. Let's put it all together. Let's walk through a real-world scenario step by step and see this silent system spring into action.
So it all starts here. Everything's fine. The grid is stable, power is flowing just like it should, and millions of these protective relays are just silently watching, waiting.
Then, it happens. A tree branch hits a high-voltage line, creating a huge fault. Instantly, the sensors on that line, these specialized devices called current transformers, they see the current spike to thousands of amps, and they scream a warning to the relay.
The relay's brain kicks into high gear. In less time than it takes you to blink, its microprocessor confirms the readings, knows this is a dangerous fault, and it issues a single, critical command: trip.
And that trip signal, that's the muscle reflex. It zips over to a massive high-speed switch called a circuit breaker. The breaker physically forces the contacts apart, creating an air gap, and that instantly cuts off the flow of all that destructive fault current.
And the result? The problem is completely contained, completely boxed in. That one faulted power line is de-energized, but the rest of the grid, it stays stable and online. That cascading failure has been stopped dead in its tracks before it could even begin. And that is how one fallen tree doesn't black out an entire city.
So, when you really step back and look at the whole picture, the importance of these devices becomes just incredibly clear.
They are truly the unseen heroes of our modern world. They operate 24/7, tucked away in substations everywhere, and their incredible speed and intelligence are what keep our power supply safe, stable, and reliable. Without them, our electrical grid as we know it, well, it just couldn't function. And that brings us to a final thought. The job of these guardians is getting even more complex. Our grid is changing fast, right? We have power flowing in all new directions from sources like wind and solar, and we're facing brand new digital threats. So the real question for the future is, how will these silent protectors need to evolve to keep our lights on tomorrow?